Our next speaker is Professor Chandra Murthy. Professor Chandra R. Murthy is a professor in the EC department of IISc Bangalore. His research interests include sparse signal recovery, its applications, and wireless communications in 5G and beyond 5G systems. Welcome, Professor Chandra Murthy. I shall hand over to you now. Thank you.
Yeah, hi. Thank you very much for the kind invitation. Can you see the slides?
Yes, they are visible.
Okay. So it's hard to, or it's a little daunting to take over after such a wonderful talk by Ayush Bhandari. But perhaps this talk is specifically focused on one little aspect that he touched upon during his talk, which is modulo compressed sensing, namely the application of the ideas he outlined in his talk to the problem of sparse signal recovery. This is joint work with my master student Dheeraj Prasannaand Chandrasekhar Sriram. And in fact, Dheeraj is the one who did most of the work here, including putting these slides together. So here's a short outline of this presentation. I'll motivate and introduce the problem of modulo compressed sensing. And then I will talk about some very basic theoretical results on recovery of sparse signals from modulo measurements. And then a couple of algorithms for recovering these sparse signals from modulo measurements. And finally, I'll talk about the specific sort of issue that Ayush mentioned throughout his talk, which is what happens if you're using a modulo-ADC and you're trying to perform sparse signal recovery. Okay, so this is the very first slide of any talk on compressed sensing. The idea of compressed sensing is to recover a high dimensional vector X, which has only a few non-zero entries from a low dimensional projection through this matrix A. So the matrix A is of size m by n. So this is the notation I'll be using throughout the talk. And X is a vector of dimension n, and therefore Y is a vector of dimension m. And the goal is to recover X from these measurements Y. And what we are told is that this vector X has only k non-zero entries. So the size of the support of X, the support is just the set of indices where the coefficient in the vector X is non-zero. So what we are told is that the size of the support of X is at most k, which is far less than n. And this area has been studied very well over the last 15-20 years. And there's a huge number of algorithms, and lots of beautiful mathematical results have been derived in this area. One assumption in all of these results is that this measurement Y is available in infinite precision. This is exactly the issue that Ayush mentioned in his talk. So in practice, one wants to convert this Y into a digital format. And for this, you would use an analog to digital converter. And an analog to digital converter works like this, that it has various step sizes, steps, and there is a step size. And any input that is beyond this maximum level lambda or minimum level minus lambda gets clipped to lambda. And in between these two levels, there is a quantization width or step size, which is given by delta. And the efficacy or how good this analog to digital converter is often captured through the dynamic range of the quantizer, which is 20 times log 10 of the ADC range, which is 2 lambda, divided by the step size, which is delta. And this is something that's going to be proportional to the number of bits you use for the quantizer. So basically, the precision of the quantizer depends on the number of bits. And of course, the important point that Ayush also mentioned in his talk is that the quantization error not only depends on this delta, but also on the value lambda, because that determines the clipping rate, how often you end up clipping the function, the input to the quantizer. And so if the measurements can only be recorded, if the measurement setup can only record amplitudes up to plus minus lambda, what happens is if you have a certain input, then the output will exactly follow the input up to lambda or minus lambda, and then it will saturate. and it will saturate to plus or minus lambda. So this figure might look familiar to you from Ayush's talk. That's because the figure has actually been stolen from one of his papers, such as down here below. Now, the issue here is that you will have a loss of information due to clipping, and so one potential approach could be to wrap around the signal so that values that go beyond this lambda gets folded back to the minus lambda to plus lambda range, and you use such a quantizer, such a sampling scheme to collect your data. And these are called self-reset ADCs. And there are also hardware prototypes that, again, Ayush showed in his presentation, that can actually perform such kind of self-reset ADC-based sampling. So that self-reset ADC, following exactly the notation again in his talk, is can be represented as Zi, which is the modulo version of the input Yi, which basically does the modulo with respect to this lambda, and then it centers it. Now, for simplicity in this talk, for the most part, I'll consider the modulo 1 operation, which is almost the same as setting lambda equal to 1 here, but we will look at Zi, which is the familiar modulo function of Yi to 1, which means it just collects the fractional part of its input. So one question that comes to mind is, if you're using such kind of a modulo or a self-reset ADC, then why not simply scale the signal? If your signal has a dynamic range that goes beyond plus minus lambda, why not just scale it down and then work with the scaled down samples, because they will be between minus lambda and lambda, and then you can process the signals without having to encounter or deal with this issue of signal clipping. And the reason you can't do that is because there is a quantization step in between that. So for example, if you have a signal with a very high dynamic range, when you scale the signal down so that it falls within the plus minus lambda range, then a lot of the detail in the signal, which is of small amplitude, will get completely lost when you do the quantization. And so the signal resolution cannot be increased by simply scaling the signal down, quantizing it, and scaling it back up. And so when you do the scaling, of course, the quantization error will then become dependent on the maximum value of the input signal. So the point is that if you use these kind of self-reset ADCs, they can reduce the quantization error. So if you have a very high dynamic range of your signal, instead of scaling it down and then sampling and then using an ADC for a lower range, which means that you lose resolution in the signal. Instead, if you do a self-reset ADC, over the small dynamic range, you have a higher resolution, and so you can help to reduce the quantization error. However, there is a loss of information due to the modulo operation, because once you've done the modulo operation, you don't know how many times the signal has folded, and you need to be able to overcome this loss of information due to this modulo operation. And the question that we look at in this talk is whether the recovery of sparse vectors is possible from modulo measurements. So this, before I talk about that, this is actually a reproduction of one of the key results that Ayush presented in his talk, which I'm going to just tell the same result to you in my own words, which is that if you're given a signal Sk, which is a k-sparse signal, think of it as a signal composed of k spikes, then if you have access to a low-pass filtered version of the signal, which is G, and then you take samples of the signal, which is G of t, sampled at t is equal to nt, capital T is the sampling period, and you take capital N such samples, but these are not normal samples, they are modulo samples of this signal, then it is if you want to recover this Sk from these samples Yn, then a sufficient condition is that t should be less than or equal to 1 over 2 pi e, and here the signal is band limited to pi, and so 1 over 2 pi e, the sampling period being less than that is sufficient, but you do need to take slightly more number of samples. So okay, so the point here is that the sampling rate is slightly higher than the Nyquist sampling rate. However, the sampling rate does not depend on lambda, and it does not depend on k. It does not depend on how many spikes there are in the signal, and it does not depend on how high up you are going to clip the signal. But the number of samples needed to recover this Sk does depend on k and this lambda as it shows up here. It also depends on the total variation in the signal through this beta g factor over here. So what we'll do is we'll think of these, or rather we'll go from these low-pass filtered measurements to compressed sensing measurements. So similar to that, the idea here is that instead of getting the measurements y equal to ax, we will get the measurements z, which is equal to the modulo version of this y. And think of this as essentially you've integrated the modulo operation into your measurement setup, so that what you get access to is these y star. So one thing I want to note here is that I am not considering the effect of quantization yet. That will come later. So at the moment, let's think of it as from between minus lambda and lambda, or rather here between 0 and 1, because I'm going to consider only the fractional part. What I get to see is exactly the signal. So in other words, a good way to think about it is that I have a fine quantizer between 0 and 1, and I'm asking whether it is better to have a fine quantizer between 0 and 1 and allow for folding, or use a coarse quantizer over a wider dynamic range, but you have no folding. So so suppose, okay, as a starting point, suppose we have measurements y star, which is the element wise modulo 1 operation, which just collects the fractional part of its input. Then and x now is as before, it's an n-dimensional vector. N is a large number, so it's a high-dimensional vector with only s non-zero entries. So that's what we mean by saying it is s sparse. And A is a measurement matrix of size m by n. So we are getting m measurements of an n-length vector which has s non-zero entries. But we don't get these measurements as the linear projection ax, but what we get to observe is ax star, which is the fractional part of ax. So the questions we want to answer are, what are conditions on A such that every S sparse vector can result in a unique Z? So potentially, if you imagine, you could build a huge table which contains all possible Z's and what X maps to that Z. And the second question is, what is the minimum number of measurements you need so that this condition will hold? How would you construct a measurement matrix A that will guarantee that the unique recovery of sparse vectors from modulo measurements? And finally, and perhaps practically most importantly, how do you solve this problem of recovering X from its modulo measurements in an efficient manner? So we'll start with some theoretical results, which are the first 2-3 questions in the previous slide, and then we'll go to some algorithms. Okay, so one simple point is that if you take any real number y, you can write it as its integer part v, which is in z, which z is the set of all integers, and a fractional part little z, which is between 0 and 1. By extending this to vectors, any vector y can be decomposed as a vector z whose entries lie in the interval 0 to 1, and a vector v whose entries are integers. Now from this we can directly see that if you only have access to z, you can add any integer vector to it and you can call that your y. You have no way of knowing which y gave rise to those fractional part measurements. And so there is obviously no one-to-one correspondence between all possible vectors y and z. However, what we have access to is not the fractional part of y, but the fractional part of ax, where x is a vector in R to the n. So the question is, and so one way to think about it is if you take the first entry of x, that first entry, because it's getting multiplied by a, it actually shows up in every entry of y. So when you're taking the fractional part of y, you're actually taking a little bit of the first entry of x in every entry of y. And so the question is, instead of taking the fractional part of x, if you've taken the fractional part of y, can you does that help in the possibility of a one-to-one correspondence between different sparse vectors in R power n and different measurement vectors, modulo measurement vectors Z. So here's a proposition. What this says is that if you're given a matrix A of size m by n and an S-sparse vector x, which is in R to the n, these two properties are equivalent. The first property says that x is the unique S-sparse solution to the problem AW equal to y. So you're solving for W here. You're looking for a W that explains your observations with, okay, I think it should be AW equal to y with with z equal to y plus an integer vector, where z itself is equal to the fractional part of ax. So, so you're looking for a w such that you can write. So, yeah. So, okay. So let me put it this way. You're given these measurements z, which is equal to the fractional part of ax. You look for a vector v in z to the m, such that if you compute z minus v, you get a vector y for which aw equal to y has a unique S-sparse solution. Now, that property is equivalent to if you were to solve this problem of minimizing the L0 norm of W, subject to AW plus V is equal to the fractional part of AX, where V is a vector in Z to the M. So here the optimization is over two variables, W and V, but the cost function only contains the L0 norm of W, which is basically counting the number of non-zero entries in W. Then, but V is showing up inside the constraint. So you're allowed to choose any V in Z to the M, and then you're looking for what is the sparsest solution you can get to AW equal to AX star minus V. And among all such sparse solutions that you find the solution that has the smallest L0 norm. And if X can be reconstructed as the unique solution to this optimization problem P0, then it is also true that X, that is point number 1 is also true. The proof of this is very easy. It follows along some similar results that one usually proves in when one starts out in compressed sensing, where one starts by asking if you're given ax equal to y and you want to solve for a sparse x, under what conditions is unique recovery of x possible, even if you could solve the or provided you could solve the NP-hard sparse recovery problem. And the arguments are actually along similar lines. So I won't, maybe I won't go over this argument, but in fact, it's actually very straightforward. If X is the unique S-sparse solution of this thing, then if you were to find a solution X hash of this problem P0, because X is already an S-sparse vector that satisfies the constraints of this P0 problem, then this X hash has to be S-sparse, and it also satisfies the same constraint that the assumption of, or the starting point of statement 1 does. It implies that by the fact that statement 1 says that X is the unique S-sparse solution, it must mean that X is equal to X hash, and of course the other way is actually direct. So that's about the one sort of simple point about the sparse recovery problem. And now let's talk about identifiability. What identifiability refers to is that if you take the set of all S-sparse vectors, x1, x2, x3, etc., each of them under modulo measurements should map to distinct observations z1, z2, z3, etc. So if this happens, then at least you know that if you're given an observation z2, there is only one vector x2, one S-sparse vector x2 that could have given rise to these observations. Now, when will this not hold? It won't hold if, for example, x1 and x2 gave rise to the same observation, that is z1 was equal to z2, which means that there is an integer vector v1 and an integer vector v2, such that ax1 plus v1 equals ax2 plus v2. So A times x1 minus x2 is equal to v2 minus v1, which is another integer vector. So when you take x1, which is an sparse vector, and x2, which is an sparse vector, and you take their difference, that will be at most 2s sparse. And so if you take the corresponding columns of A, they should not have an integer vector in their range space. If that happens, then if that is true, then all distinct sparse vectors will map to distinct outputs under modulo measurements. So based on this very simple observation, we have the lemma that any vector x satisfying L0 norm of x, or having at most s non-zero entries, is a unique solution to the optimization problem P0, is equivalent to saying that any 2s columns of the matrix A are linearly independent of all v in z to the m. Of course, you have to remove the zero vector because nothing is linearly independent of the zero vector. So to just compare this result with compressed sensing, this corollary breaks this necessary and sufficient condition down into two points that are necessary. The first point is that the number of measurements m must be greater than or equal to 2s plus 1, which is just one extra measurement compared to what is compared to the necessary and sufficient condition in the classical compressed sensing algorithm, which does not have modulo measurements. And the second condition is that any 2s columns of the matrix A must be linearly independent, and that's the same as the requirement in compressed sensing. So the main point here is that compared to classical compressed sensing, you just need one extra measurement for identifiability of sparse vectors from modulo measurements. Now, the next thing is that, yes, it is identifiable, but is m greater than or equal to 2s plus 1, is it sufficient? So the answer is that if for any n greater than or equal to 2s plus 1, in fact, we're going to consider, or we typically consider n to be very large, so it's a very mild condition. There exists a measurement matrix A of size m by n with m equal to 2s plus 1, so you don't need any more than 2s plus 1, such that every sparse vector x in R to the n can be reconstructed from its modulo measurements z as a solution of the P0 optimization problem. So I'm setting aside the complexity of solving the P0 optimization problem. It is NP hard, but if you were able to solve the P0 optimization problem, then there exists a measurement matrix A which will ensure that you will always recover an sparse vector x from its modulo measurements. So basically 2s plus 1 is sufficient. The idea of the proof again follows exactly along the lines of classical results in compressed sensing in terms of sufficiency of 2s measurements in the case of compressed sensing. So if you're given an A matrix which has 2s plus 1 rows, what you do is that you take any u in z to the m and a set S whose size is at most 2 times little s. Then you construct this matrix BUS, which is equal to u and the column u, the vector u, and concatenate the columns of A indexed by this set S next to it. So this will then become, there are S columns, or sorry, there are 2 S columns here, and there's one column here. So there are 2S plus 1 columns, and then there are 2S plus 1 rows. So this is a square matrix. If the determinant of the square matrix is 0, then this condition is not satisfied, namely that the columns of AS are not linearly independent of an integer vector u, and so unique recovery of sparse S-sparse vectors is not guaranteed. So this condition, that determinant of BUS equal to 0, is basically a polynomial condition in the entries of AS, and therefore the set of matrices A such that determinant of BUS equals 0 is a set whose Lebesgue measure is 0. And now if you take the union of this over all u in z to the m and over all sets S with at most 2 times smallest number of indices, then this is actually a finite union, and the inner union is a countably infinite union. And so such unions of sets of Lebesgue measure 0 is still a Lebesgue measure 0 set. So you can choose any A outside this set of Lebesgue measure 0, and that A will work. So for example, if you use Gaussian random matrices, it is outside the Lebesgue measure 0 set, and so is any matrix drawn from a continuous distribution. And so, on the other hand, integer matrices will not work. That's because if you take the integer part of, so if you take an integer vector A and any x in R to the k, then if you take the um, integer part of A transpose times the, if you take the fractional part of A transpose times the fractional part of x, that is the same as A transpose, that is the same as the fractional part of A transpose times x. And so you cannot distinguish between x star and x by using such measurements. And so this is actually from this paper, in which I think also Ayush referred to in his talk. So integer matrices will not work for recovering sparse vectors from modulo measurements. So now let's talk a little bit about algorithms. There's related work on phase unwrapping and generalized approximate message passing. In phase unwrapping, basically you relate the problem of recovering sparse vectors from modulo measurements to the phase retrieval problem. And it's actually a two-stage algorithm, and then there's an alternating minimization framework that they consider. And in the GAMP approach, it's a Bayesian approach where you impose a Bernoulli Gaussian prior on this vector x that you are trying to recover, and then you develop a GAMP algorithm. So these are also very recent developments in the topic. So now let's talk about, the one nice thing about the way we've approached the problem is that we've come at it from, the path is actually mirroring the development of compressed sensing and compressed sensing based recovery algorithms. So we can exactly follow the same pathway as with classical compressed sensing, namely that now we are faced with this problem P0, okay, which is to minimize the L0 norm of x, subject to ax equal to z plus v. Z is our observations that are given to us, and v is any vector in z to the m. That is our problem P0. And again, to relate this to the compressed sensing problem, in the compressed sensing problem, there is no v. So just delete v throughout in this problem. That's the P0 problem of compressed sensing. And in compressed sensing, instead of solving this P0 problem, we replace this L0 norm of x with the L1 norm of x and convert it to a convex optimization problem, which is easy to solve. In fact, that problem can be posed as a linear program. So following the same approach, what we can do is to replace the L0 norm with the L1 norm, but you still have this v in the modulo compressed sensing recovery problem, and we'll call this problem P1. And now this is still a combinatorial or a mixed integer optimization problem because of the presence of this v, which is an integer vector in the optimization problem. So in order to say something about when this will succeed, we can also define what is known as an integer range space property, where what this says is that the matrix A is said to satisfy and the integer range space property of order S if for all subsets of the index set 1 to n of size at most little s, if you take the L1 norm of u, the entries of u indexed by s, that is smaller than, it should be smaller than the L1 norm of the entries of u indexed by the set S complement, and this should hold for all u which are such that AU is an integer vector. Now relating this to the compressed sensing literature again, if V is just equal to 0, that is, you're looking at all vectors u in the null space of A, that is what is called the null space property in the compressed sensing literature. Now we want that kind of null space property to hold for all u such that AU is an integer vector, not just the all zero vector. So then if that happens, we say that the matrix A satisfies the integer range space property. Unfortunately, there is no verifiable, it's not easy to verify whether a matrix A satisfies this integer range space property, which is the same as the null space property in the compressed sensing literature. There is no easy way of verifying whether a matrix satisfies the null space property or not either. However, one can say that uh, if the matrix A, so the matrix A satisfying the integer range space property is necessary and sufficient for every S sparse vector X to be a unique solution of the problem P1. Okay, so at least we have a condition under which is an if and only if condition for unique recovery of S sparse vector by solving the problem P1. And how to design matrices A such that this integer range space property is satisfied is an open problem. So now, to make the problem a little more tractable, we can consider the measurements being restricted to 2K modulo periods. So suppose we have some potentially fairly loose upper bound on how big this entries of AX can be. And so if we knew that the entries of AX, L infinity norm, is at most equal to K, then we can solve the same problem P1 as before, but with this extra constraint that AX L infinity norm is at most equal to K. We'll call this P1K, and we'll look at the following class of problems where we restrict so instead of considering the integer range space property where we are considering all possible integer vectors. So you see here this V could be any integer vector. So we'll look at an L restricted range space property where the same condition as before, that is US L1 must be less than US complement L1 must hold, but for all vectors belonging to the set L, which is a subset of this set that I had in the previous slide. Now, if I say I fix the set L to contain only the vectors U that lie in the null space of A, then this L restricted IRSP reduces to the null space property in the compressed sensing literature. Now, if I take L to be equal to this set itself, then it reduces back to what I had in the previous slide. Now, let's define three different sets. L sub L is the set of all U such that AU is an integer vector, but this integer, the entries of the integer vector are at most equal to the small l. Then this KLS is the set of U such that AU is an integer vector, and A times U on this support set S, the L infinity norm is at most L, and again AU as complement L infinity norm is also less than L. And finally, KL is the union of these sets KLS over all possible sets of size small s. Okay, there's a note that these sets can be, some of these sets can be are contained in other sets, but this is not very crucial for the purposes of this talk. Now, these are some slightly abstract definitions, but here's a result on how these definitions are useful. So if you're given a matrix A of size m by n, then the guarantees of the for unique recovery of every sparse vector as a solution to this problem P1K in the previous slide, with the additional constraint that the L infinity norm or the largest entry of AX is at most K, are that a necessary condition is that A should satisfy this KK restricted IRSP, and a sufficient condition is that A should satisfy L to K minus 1 restricted IRSP. So, so because we are looking at a potentially computationally simpler algorithm P1K to solve the problem, now there is a gap between the necessary and sufficient conditions. Okay, and because of these containment notes here, the necessary condition is of course weaker than the sufficient condition. Okay, and if as K tends to infinity, both these sets become the L, what did I call it? This set here, and so then both of them they reduce to the IRSP, and we get that the IRSP is both necessary and sufficient. Okay, I'll talk about now the reason to introduce that K restricted IRSP and the fact that AX L infinity norm is less than K is because we can then use a mixed integer linear program to solve this problem. So note that the L1 norm is the sum of the absolute values of the entries of a vector, and I can write that as the sum of uh, the positive components of the vector plus the sum of the negative components of the vector. So this the first set, which is the set of indices for which xi is greater than 0, we'll call that I will collect those entries of x into this vector x plus, and the set of vectors, set of entries for which the xi is less than 0, we'll take those entries of x and we'll collect the negative of those values in x minus. So both x plus and x minus are non-negative vectors, and they also have non-overlapping support, and x is actually equal to x plus minus x minus. Now, because of this constraint that the largest entry of AX is at most K, we have that the integer vector that we are looking for has entries between minus K and plus K minus 1. And therefore, we can reformulate this P1K problem we had earlier as this modulo mixed integer linear program, where we want to minimize 1 transpose times x plus x minus. So it's a linear function of x plus and x minus. And then these x plus and x minus are stacked in like this with this vector v to say that you need to be able to explain your observation z. And this vector v is any vector with integer valued entries bounded between, the entries are bounded between minus k and k minus 1. Okay, and x plus and x minus are non-negative vectors. Now, these kind of mixed integer linear programs, there are lots of algorithms to solve them. In fact, MATLAB itself has a toolbox. In the optimization toolbox, it has an int probe function that can be used to solve these problems. Of course, as k increases, this function will take longer to solve, but in principle, these are relatively easier to solve than the problem P1K with k tending to infinity. So if you use that and then you look at the phase transition diagram of sparse recovery, so I'll explain that in a moment. So here what we've considered is that you're given vectors of length 50, and the measurement matrix A has Gaussian 0 mean 1 over m variance entries, and the non-zero entries of x are uniformly distributed over the range -1 to 1. And what we do is we vary the sparsity level, which is defined as rho, which is s, the sparsity level divided by n, and we vary the number of measurements. M over n is delta. So if delta equals 1, then you are getting n measurements for an n length vector. For delta less than 1, it becomes an underdetermined system of linear equations. And again, as s, if for example s equal to 1, then rho is 1 over 50 here, which is 0.02, so somewhere here. And so basically, this is a color plot which shows where yellow represents 100% recovery and dark blue means 0% recovery. And this is a typical phase transition diagram where we see that for if you have too high a sparsity and too few measurements, then the recovery will fail. If you have a low enough sparsity and sufficiently many measurements, the recovery will be successful, and there's a sharp transition from one to the other. And if you overlay the 2s plus 1 theoretical boundary that we had earlier, that looks sort of passes right through the transition region of this phase transition diagram. And so we can also look at what is the effect of the variance of the input signal. And what we show here is, so again, this is the phase transition, but plotted as just the boundary of the phase transition is plotted for different input distributions. And once again, if you take, for example, a sparsity level of 6, and if you take these curves here, these correspond to uniform between -1 and 1, or uniform between -0.5 and 0.5. So fewer measurements are enough, but as the variance of the input increases, if it is uniform between -2 and 2 or Gaussian zero mean unit variance, you need higher number of measurements. So you get good performance for signals with low variance, and as the variance of the input signal increases, the number of measurements required is slightly higher. So now let's talk about the ADC effects and what happens with modulo ADC in the context of compressed sensing. So when you have modulo measurements, you so now what we are looking at is we not only have modulo measurements, but we also have quantized version of the output of these modulo measurements. So we will then be applying a quantizer on the after passing the signal yi through a modulo operation. Now, so for the quantizer, we will just consider a uniform quantizer for simplicity, using L bits over the range minus lambda to lambda. And yi is the ith entry of ax. So just for comparison's sake, I will consider this function f lambda here. I'll consider different options for it. Of course, one option is the modulo measurements that we've been discussing so far, which is f lambda of I is the modulo version of this yi, which is what we call modulo ADC. But for comparison purposes, if you use a traditional sampling scheme, you will end up with clipped measurements. That is, f lambda of yi will get clipped to lambda or minus lambda if yi is greater than lambda or yi is less than minus lambda respectively. Otherwise, you will just get yi, and then you will pass that yi through this quantizer. Another way to do this is to scale the measurements, which is to apply a scaling on these yi's, such that this 1 over alpha times yi is always within this range minus lambda to lambda. And so beyond that, you will only get the quantization error because you're quantizing the 1 over alpha times yi to L bits. Now we'll choose alpha to be 1 over lambda times the maximum value of yi, which is of course not realizable in practice because a priori you don't know what the maximum entry of all the vectors you might want to quantize is. But this is just for comparison purposes. So we are giving the option of scaling as much advantage as it can possibly get. So with scaled measurements, because there is no modulo happening, we can simply solve the linear program which asks for the smallest L1 norm vector that explains your observations with x plus and x minus being greater than or equal to 0. This is simply the L1 relaxation of the sparse recovery algorithm in this case. But the difference is that Z is now your quantized measurements instead of the unquantized measurements. For the case of where you have clipped measurements, there are actually a couple of methods that were explored in this paper down below. The first is a rejection-based approach where you can look at the vector Z and see which entries have got saturated. And you can simply discard those saturated measurements, and you can run this linear program that you were running for the scaled measurements on the remaining measurements. The other approach is slightly more sophisticated. All it does is that in addition to running the LP, it also imposes a constraint that the remaining measurements should satisfy the fact that they were getting clipped. So the ones that get clipped to plus lambda, you want to ensure that when you take phi s plus times x, that will give you entries that are greater than lambda. The ones that got clipped to minus lambda, if you take phi s minus times x, those are going to be less than minus lambda. So this just makes sure that the vector x that you recover is consistent with the clipped measurements, although you're not taking the clipped measurements into account other than the consistency constraint. And with the modulo measurements, we will run our MILP algorithm that I just presented to you. So the default parameters, unless otherwise stated, again, we will take 50 length vectors with 4 non-zero entries and 30 measurements. And we'll quantize each measurement to 6 bits, and we'll take lambda to be 0.5. This is the clipping height of the quantizer. And then we will again generate our measurement matrix A with IID 0 mean 1 over M variance entries, and the support indices, that the indices of x that correspond to its non-zero entries are drawn uniformly at random from all possible entries from 1 to n, and the non-zero entries are considered to be Gaussian distributed with zero mean and unit variance. So what we'll do is we'll first calculate the instantaneous normalized mean squared error for each Monte Carlo run, which is the error between the true x and the x that is output by the algorithm norm square divided by the norm of x square. And we'll say that the recovery is successful if the instantaneous normalized mean squared error is less than some threshold 0.1 in the unquantized case. So the reason for doing this is because, so when you take these modulo measurements, sometimes the sparse recovery algorithm will fail, and when it fails, it will actually output a dense vector. And by looking at the vector, you already know that this is not the correct answer, and you can actually potentially discard such cases or declare a failure. And so what we'll do is we'll consider two different aspects. One is the probability of error or probability of failure, which is the number of Monte Carlo runs with unsuccessful recovery divided by the total number of Monte Carlo runs. And then we'll also look at the average success NMSE, which is the average of the instantaneous NMSE for the cases where the recovery was successful. So if we look at that, what is shown in this plot is on the x-axis is the number of quantization bits, on the y-axis is the normalized mean squared error. And first of all, if you simply compute the average normalized mean squared error, then both the LP and the MILP will show a flooring. Okay, and that's because, as I said, even if you have a higher number of quantization bits, because of the folding, sometimes the recovery will fail, and when it fails, it will fail miserably, and you'll accumulate a very large normalized mean squared error, and that leads to a saturation at higher number of quantization bits. However, if you look at the mean squared error in the cases where the recovery was successful, then as you increase the number of quantization bits, the normalized mean squared error in dB decreases linearly with the number of quantization bits, which is very appealing or very intuitively satisfying from a compression point of view. If you've looked at signal compression and you're looking at the effect of quantization, often you will see plots where the normalized mean squared error drops linearly with the number of quantization bits. And that's the expected behavior of a good quantizer. The one thing to note is that in order to get a plot like this, where the NMSE is linearly decreasing with the number of quantization bits, in the case of the rejection LP, I need to throw away about 12% of the Monte Carlo runs. However, with the MILP, I only need to throw away 1% of the Monte Carlo runs, and then I get this red curve down here. So the probability of error with the MILP is much lower than that of the rejection LP. This slide presents the sort of complementary point of view, which is how does the probability of error vary as a function of the range of the ADC parameter lambda. So what you would expect is that as you increase the range of the ADC parameter lambda, your quantization error, you will have less folding of the signal. And because there is less folding of the signal, the probability of error actually decreases as you increase the range parameter lambda. So that's what is mentioned here. The probability of error decreases with the range due to lesser folding. But then you also see the effect of the number of measurements as you go from 15 measurements to 25 measurements to 35 measurements. The performance improves, and in fact, the MILP often offers an order of magnitude lower probability of error compared to the rejection LP. It is also compared with another the linear programming based approach, but the linear programming based approach is not really accounting for the folding, and so its performance doesn't really change much with the range parameter lambda. Now, here's another interesting plot, which is something we would like to investigate in more theoretical depth going forward, which shows the average success in MSc as a function of the ADC range parameter lambda. Now, what we see is that for 3, 4, and 5 bits, the normalized mean squared error actually decreases as the range parameter lambda increases. Of course, later it starts increasing again, but at least initially, as you increase the range parameter lambda, it decreases. Whereas for the other cases, it's actually only increasing, which means that in these cases, you're actually better off incurring more folding and having a lower range parameter and quantizing more accurately. So if you've signed up for a 10-bit quantizer, then it's better to have a lower range parameter and incur more folding, and that helps to achieve a lower success in MSc compared to if you had a higher range parameter. But also interesting to note is that, so for example, if I take this blue curve and I look at what happens at lambda equals 0.8, I get a success NMSE which is actually higher than the success NMSE I can get with just 7-bit quantization, but with a lower range parameter lambda. So there is an interesting trade-off between the number of bits of quantization, the quantizer range, and the quantizer clipping threshold lambda, which is certainly worth exploring further as we go further. So these are actually very new results which Dheeraj, this simulation results that Dheeraj generated pretty much in the last week or two, and so these are very fresh results that we are in the process of trying to understand and investigate further. So this brings me more or less to the end of the talk. So to summarize, modulo-CS measurements are actually identifiable, and the penalty is just one extra measurement compared to classical compressed sensing. And Gaussian random matrices work well as candidate measurement matrices for modulo-CS as well. And we presented one algorithm, which is the mixed integer linear program based algorithm, which can be used for modulo recovery. And under certain conditions, these modulo ADCs can lead to lower quantization errors and better recovery compared to uh, expanding the dynamic range of your ADC and incurring larger quantization errors. And the next things that we are looking at is extending these algorithms to the noisy case, developing more interesting Bayesian algorithms, and also to understand the trade-off between the number of folds and the number of quantization levels. Thank you very much for your time. I'm happy to take questions.
Thank you, Professor Chandramurthy, for this wonderful and informative talk. Does the audience have any questions? If you have, you can go ahead and raise your hand. I'll then ask you to unmute and ask your question.
Yeah,
Yes,
Yeah,
Dr.
sure. Thank you.
Ayush, please go ahead.
Yeah, it's good to see a talk when you have only read a paper because, at least for me, I don't get much from the paper. Thank you for the explanation. One question I would ask to you, which I get asked a lot all the time, is that how does the machinery scale to dimensions such as 2 and 3? Because the general perception may be that these kinds of things are very well suited for imaging tasks. So if you have,
so
let's say, if
dimensions
you have
two
a
or three, meaning?
yes,
Oh, okay,
yes.
okay.
So
So,
if you want to do, let's say you want to scale this, like I mentioned, for tomography or things like these, people are actually trying to build alternative setups, and I think that motivation is very clear and very interesting, I would say, because it's a very important driving force for investigating. So I was just wondering, what would you have any inclination
no.
around the top?
So that's a very good question. So honestly, I have not thought about this at all.
Okay, okay,
So I'll need to think about it. But it's a good
yes.
question. Thanks
This
for the question. Yeah.
The second thing you mentioned was identifying that when the dynamic range increases, or let's say you bring the for the fixed amplitude you bring the lambda parameter down. I
Mhm.
think one thing at least in statistics, has not been realized completely is that the effect of folding distributions. So a Gaussian distribution may become uniform if you apply it, if you pass it through modulo nonlinearity.
Yes.
So I think this is something which maybe is very relevant to your observation that when you have this clipping, when you are clipping further, in fact, it starts to benefit you because you are going from a hypothesis, unbounded noise hypothesis, which is Gaussian, to a bounded noise hypothesis.
Mm, mm.
So
Yeah,
it's
yeah.
something I mean, it's not something I'm like, it's not something I've paid attention to, but I think it's something that you constantly see when you run experiments that
Yes.
with
Yes.
even with structured things. So something to something to see. Okay, that's all I wanted to say. Thank you.
Yeah, yeah, yeah. Thank you. Both excellent points. Thank you very much.
Are there any other questions from the audience? Okay, so there seems to be no more questions. Thank you, Professor Murthy, and on behalf of IEEE-IISc Communications Society, kindly accept this plaque as a token of our appreciation for such an informative talk.
Thank you very much. And I hope I've earned the privilege of your time, as somebody else said in a very popular movie.
Yes, sir.